Good morning, class. Welcome to our third lecture. To this point, we've been introduced to the topic of heat transfer, and we've gone over the three rate equations: Fourier's law, Newton's law of cooling, Stefan Boltzmann's law. We've gone into more detail about Fourier's law. We've looked at thermal conductivity, which is a key material property that shows up in Fourier's law. So today we're going to look at the heat equation. So the heat equation is basically the governing differential equation for heat transfer problems. We're going to go through it. We're going to derive the heat equation. We're going to talk about the different aspects of the heat equation. And then we're going to work a few examples that help drive home a few points about the heat equation. So basically in this class, I've said this before, but the class is really about energy balances, and the difference between thermodynamics and heat transfer is that in one case, thermodynamics, we're balancing energy in joules, and when it comes to heat transfer, we're dealing with rates of energy transfer and the processes that are involved in moving a system from state 1 to state 2. So we talked about control volume energy balances. Energy balances drawn around control volume. So we talked about energy balances drawn at surfaces. So in order to derive the heat diffusion equation, we're going to draw an energy balance around a control volume. So what we're going to take is we're going to take this square here, and we're going to take a square volume. So we're going to work in Cartesian coordinates. An infinitesimally small square volume, and we're going to take as many of these squares. So we're going to take our medium and we're going to divide it into an infinite number of these small squares. So you can imagine as these small squares approach a zero volume, then we approach solving for energy balances at discrete points inside of our medium. All right, so now we have our square. So we have our square here, and let's blow up our square control volume and apply an energy balance to it. So nothing new here. We're just going to go E in minus E out plus energy generated equals energy stored. So we have this control volume. So you should have your notes out. They're posted on T-Square, so you should print your notes out and work along with me here. And you can see it a lot better in your notes. So some of the things won't show up very well on the board because of the video, but they should show up pretty well in your notes. So we have this square. We're working in three-dimensional spaces. So we're deriving the most general form of the heat equation. And so what do we have that's important here? Well, we have heat that can be conducted into this volume. So this is the energy in. And the heat that can be conducted in the x direction, in the z direction, and in the y direction. So energy enters in those three directions, but energy also can leave. So energy can leave in the x, y, and z direction. So here we have that represented as a heat rate Q with a subscript x, y, or z for energy entering the control volume. And then we have a heat rate Q with subscript x, y, z plus a delta x, delta y, delta z. And what that basically means is that there's some change in the energy or the heat rate from the entrance point to the exit point in the same axial coordinate system. So we have energy coming in, qx, energy leaving, qx plus delta x. And the same thing for the y and the z directions. So that basically balances our energy in minus energy out. Now we have our energy generated and our energy stored. So these are volumetric quantities. So they happen over the entire volume. The energy in, the energy out happens on the surfaces. So we basically have surface energy balances describing the energy going in and the energy coming out. But it's a volumetric process of storing energy or generating energy. So heat transfer is about dealing with the energy in minus the energy out. And basically here, we're going to plug in the conduction rate equation. So we're choosing the conduction rate equation, not the convection and not the radiation equation. Because remember, this is a solid material. So in a solid material, heat transfers by conduction, molecular diffusion. Radiation and convection occur on the outer surfaces of a medium or a body. But we're dealing right now with the inner surfaces, these inner control volumes. So the energy in and energy out are always going to be a balance of conduction rate equations. So here we have our energy in. And I mentioned previously, energy in equals the sum of all of the conducted energy in, Qx, Qy, Qz. Those are heat rates. And the energy out is equal to, here in the x direction, our heat rate Q sub x, plus the amount of change in that Q sub x over the differential distance in the x direction, dx. So we have this partial derivative of Qx with respect to x times dx. So that's the change in the heat rate with respect to x times the distance over which that change happened, dx. And we have the same thing occurring here for the y and for the z direction, where we have leaving the system the amount that was put in, Qx, plus the change that happened over that control volume, or within that control volume, coming out. So here we have what was put in, and this is the change in the control volume, and together they sum to equal what's coming out. So you take these and you put them together in the form of energy in minus energy out. What you see here is that the Q sub x, Q sub y, Q sub z's, they cancel each other out. So basically what this statement now is saying is that the energy in minus the energy out equals the change in energy over the control volume. So we're just left with these derivatives, as you would expect. And they're partial derivatives, because this is a three-dimensional problem. They're partial derivatives. Right. So now we're stuck here. Let me take a step back. We have here Q's. So we're taking partial derivatives of the heat rate with respect to x times the geometrical distance dx. So let me distinguish here the dx, dy, dz from the partial x, partial y, partial z that show up in the partial derivative. So the dx, dy, dz that's the geometry, the dimensions of our finite volume, where the partial derivative with respect to x, y, and z is actually the rate of change. So you're just to make a mathematical distinction. So we're talking about Q, but what we really want to talk about is what Q equals. And I talked about before, for Q, in this case, for the heat equation, Q is going to be the conduction rate equation. So the next thing we want to do is we want to look at the conduction rate equation again. We want to look at Fourier's law, conduction rate equation, and we want to look at it in the three different directions. The x direction, so Fourier's law, once again, minus k in the x direction, dy, dz, partial derivative of t with respect to x. So remember, we're taking partial derivatives here still because we're working in three-dimensional space. And then we can have the same thing for the y and for the z direction.